Welcome to my presentation about gravitational waves, where the Nobel Prize was given for in year 2017. So let's first go through the table of contents. I first want to briefly talk about the historical context of the topic of gravitational waves and then also explain these gravitational waves to you. Then I'll tell you something about the first observations, which then later on led to the LIGO detector. We then look at the results of the measurements of LIGO and of course also its difficulties and problems that appear. And then in the end I would like to introduce the Nobel laureate and also give you a little outlook on what is going on in the research of this field. Einstein said in his theory of gravity in 1915 that space and time belong together and that gravitation is like a distortion of this space-time. You can think of it as a stretched towel on which you place a heavy ball, and then this ball bends the towel, which stands for the space-time, and of course the heavier the ball is, the more the towel gets bent. The theory of gravity expanded the theory of special relativity that he published about 10 years earlier. And as we know, there he didn't involve the effect of gravity. Later on then, in 1918, he wrote this paper here, you can see on the picture, called Über Gravitationswellen. And here he says that every moving masses are sending out special waves which disturb his described space-time. He calls the force of gravity in this paper as being the curvature of space-time. Furthermore, he made a prediction back then that these waves will never be measurable. But of course today we know that he was wrong with this. The first time that an indirect proof was made was in 1974 by Hulse and Taylor. And then in 1979 I think they published their discovery. And then in 2015 the first gravitational wave was measured by the LIGO detector, which I will talk about later on. So let's now take a closer look on the gravitational wave. Gravitational waves actually are propagating distortions of the spatial geometry. You can see on the animation on the left the propagation of a gravitational wave. They are transverse waves, which means that they move perpendicular to the direction of its propagation. We can make the link to electromagnetic waves, which are space and time dependent waves of electric and magnetic fields. Gravitational waves, on the other hand, are waves in the fabric of Einstein's described space-time. Both waves travel with the speed of light and can be polarized. Furthermore, electromagnetic waves can easily be produced and detected in laboratories, but the gravitational waves interact very weakly with matter and therefore they are difficult to detect. We can compare these waves and see that there are a few similarities. And it was Maxwell who once described the equations of electromagnetic theory and was then able to show that the electric and magnetic fields satisfy the wave equation when there are no electric charges or currents present. Same is valid also in the case of gravitation. And another similarity is that they both travel with the speed of light in vacuum. To see the differences, we can say that a major difference between these waves is that the gravitational wave equation works only when the gravitational field is very weak, while the wave equation for the electromagnetic fields even works with a field strength that is arbitrarily large. Another big difference is that electromagnetic waves get affected by matter and therefore cannot propagate over very long distances without losing intensity. Gravitational waves, on the other hand, are unaffected by matter, and so they can travel very long distances. This is mainly because the gravitational field is very weak, or the gravitational force, and therefore don't significantly interact with any matter. It is also to say that the wavelength of gravitational waves is more than a few kilometers, while electromagnetic waves are always smaller and can even be smaller than the size of an atomic nucleus. The sources of gravitational waves are usually very massive cosmic sources with large accelerations. They are produced by time-varying quadrupole moments, which means that this is a non-spherical motion of objects. This can also be shown by a detailed analysis of the gravitational wave equation. So, therefore, a perfect symmetric object, just for example like a supernova, would not produce gravitational waves. Or similarly, we can also say, for example, a cylinder or a disk of matter which rotates around the axis of symmetry cannot emit gravitational radiation because of this symmetry. Sources of gravitational waves can be pulsars, which is a very fast rotating neutron star, or another example is are mergers of black holes or also neutron stars. On this slide you can see a visualization of the effect of a gravitational wave. Let's imagine a plane in space consisting of these little squares, which are infinitesimal test masses. It is important to say that these masses are freely falling, so that means that no other force than gravitation is acting on them. Now, if a gravitational wave is coming along a direction normal to the plane, the open squares, which stand for the position before the wave passes by, are shifted to the position of the filled squares and then back again. Here we can see an example for a source of gravitational waves. On this animation we can see the merger of two black holes and also the gravitational waves that they produce. It is a simulation of a real event that was detected by LIGO in 2015. The two black holes here you can see were 14 respectively 8 times the mass of the Sun, and after they emerged the resulting black hole was 21 times the mass of the Sun. So this means that one solar mass was converted into gravitational waves. Now I'd like to talk about the first trials and then also observations of gravitational waves. On the left, on this picture, you can see Joseph Weber working on his detector. That was in the 1960s. And these are so-called Weber bars, these cylindrical detectors. And later on, there were already interferometers invented, but the problem with these detectors was that the sensitivity was much too small to detect any gravitational event. The first measurement of gravitational waves was indirectly made, and it happens through the study of a binary pulsar. A pulsar is a lone neutron star with a very high magnetic field and rapid rotation. And this results in radio pulses, which then leads to the name of the pulsar. And these pulses are in a narrow beam, and of course to measure it we have to be exactly in this beam to detect anything. The result then was that they measured the energy loss of the motions of the pulsar, and this energy decrease of the period was exactly consistent with the prediction by Einstein's gravitational theory. Of course, the size of the pulsar's orbit and the period decreased according to the energy loss in the form of gravitational waves. Later then, in 1993, Russell Hulse and Joseph Taylor received the Nobel Prize for the so-called discovery of a pulsar orbiting around a neutron star based on their work in 1974. Let me now come to the core of this whole detection of gravitational waves, which is the LIGO detector. LIGO stands for Laser Interferometer Gravitational Wave Observatory, and it was finished in 1999. After that, they started with the first measurements from 2002 for about 8 years until 2010. But in this period, no gravitational wave was measured. After that, they made huge improvements of the Hall detectors, and from this moment on, we call it Advanced LIGO, and they started to measure again in 2015. Today, scientists from more than 40 institutes are involved, and part of the LIGO, the so-called LIGO Scientific Collaboration, LSC. Here from University of Zurich, we have Professor Jetzer and this group, which is the only group from Switzerland that is part of this LSC. This advanced LIGO, the second generation detector, was then the first detector which was able to discover a gravitational wave. And I will talk about this later on. On the picture here, we can see the detector from Hanford. There is another one standing in the US in Livingston. And today there is also another interferometer in Europe, which is called Virgo. And it has actually the same principle, was mainly built by Italy and France. And it is to say that the advantage of having 3 or even more interferometers is that the localization of the source of the gravitational wave is much more precise, and it's easier to tell where this wave is coming from. To measure the gravitational waves, an interferometer is used, which is actually based on the Michelson interferometer, which we have already seen, I guess, in physics 3 or 4. And the principle is that a laser beam is split into 2 parts, and then it is sent into through these tubes here, which exactly have the same length of 4 kilometers in the case of LIGO. At the end of the tubes, the laser beam gets reflected and sent back to its origin. And the mirrors there, they are cooled down just to reduce the thermal distortion. Here we see when the laser beams are coming back, the setup is built in a way that these reflected light beams exactly cancel each other out. So this means if there is no distortion of the beam, they cancel out and the detector won't measure anything. Furthermore, it is to say that the detector is made that the laser beams are reflected actually back and forth for about 300 times, which increases the length of each arm to about 1,200 kilometers. Now, if a gravitational wave comes along, it distorts space and therefore the length of the tube changes. One arm becomes a little bit longer and the other a little shorter, as you can see here. Then the other arm gets shorter and this arm gets longer, and they get stretched and squeezed. And this happens until the wave has passed. Now, due to this change in distance, the alignment of the two light waves changes, and therefore some light does now reach the detector here, with an intensity depending on the gravitational wave. So when measuring this intensity on the detector, they are actually measuring gravitational waves. Now, there are a few very difficult tasks to build such a huge detector. One thing is that the laser beam must really have one exact wavelength, which is 1064 nanometers here at LIGO. The other thing is that the change in length of the two beams is very small, around 10 to the minus 18 meters. So the two reflected beams at the detector are only slightly darker and brighter, and therefore it has to be measured very precise. To measure these tiny differences in length, also the mirrors are mounted in a special way. They cannot be fixed mounted, such that only gravitational force is acting on them, and they don't move in a horizontal direction. Therefore they are fixed with a suspension system that you can see here on figure 9, and such that the mirrors can act as free particles. To really have no other distortion than gravitational waves, there is also a high vacuum necessary in the tubes, which have a volume of about 10 million liters. By the way, there is only one bigger evacuated volume, which is the LHC in CERN. Furthermore, the vacuum is necessary that no molecules collide with the mirrors, which would produce a motion of them. Since the resulting signal is very weak, the detectors have to be very sensitive. On the lower figure, on figure 10, we can see on the sensitivity of the detectors. The dark red curve is the one detector at Hanford, and the light red is the one from Livingston. And as we can see, the curves lie very close together. This means that a signal of gravitational waves can only be detected if it lies over these curves, since these curves are the sensitivity. So, as we can see on the graph, the detectors are most sensitive in the range of 100 to about 300 Hertz. The green curve there shows the sensitivity of the detectors from the first generation, just for a comparison. So what they actually measure at LIGO is the strain, which is the net displacement between the two arms. This is given by the change in length divided by the length and lies around these 10 to the minus 18 meters that I mentioned before. Obviously, we can see that longer arms would make the result much more clear and finally also easier to detect signals. Due to this really high sensitivity, it is also an important thing to measure noises and then also reduce them by filtering it out. If for example someone walks close to the arms, they register this noise and can filter the signal out. Also winds or tidal motions lead to seismic motion, which has to be filtered. Another problem is that there's also a disturbance when the laser beam slightly hits the mirrors. This affects the random motion of particles in the mirrors, which leads then to thermal noise. This is also called the Brownian noise. Let's have a look at the first detection named GW150914, which of course is named after the date of the event. It was in September 2015, and it only lasted for about 0.2 seconds, but the shape of the signal really was as expected from Einstein's theory. It was made by both detectors in Hanford and Livingston, and you can see in figure 11 that it would take about 10 milliseconds for light to travel this distance between. So therefore they had to do a time shift. You can see this in figure 12 in the upper two graphs, where they shifted the signal from Livingston, and then they were able to compare the signals. And as we can see, they really look very similar. Below this, we can see the frequency, which went from about 35 to 250 Hertz. This event here was a merge of two black holes, and they have calculated that the two black holes in the beginning were about 36 and 29 solar masses, and after the merge it was one big black hole with about 62 solar masses. So if we take this difference, we see that the gravitational waves they had an energy of about 3 solar masses. And to calculate the energy coming from these masses, we can use Einstein's formula E is equal to mc squared. Furthermore, the distance between the two black holes can be calculated with these signals they detected, since it is inverse proportional to the amplitude. Now I quickly want to introduce to you the Nobel laureates, which were Rainer Weiss, Barry C. Barish and Kip Thorne. The Nobel Prize in Physics for 2017 was awarded to these three. You can see the prize share was that Rainer Weiss got half of the prize and the rest 1/4 each to Barish and Thorne. Rainer Weiss was born in Germany, but then they fled to the US in 1938. Barish is also from the US, and he was the director of LIGO for about 8 years. Thorne is furthermore known for his extensive work on gravity and relativistic astrophysics, and he's also a professor from the US. Let me finally come to the outlook, and here I want to mention that today also other detectors such as Virgo in Europe or Kaga in Japan have been launched. And of course, the more detectors there are, the more precise one will be able to detect the source of the gravitational waves. There is another detector planned to be located in Europe called Einstein telescope. It's actually the similar principle, but the whole detector will be buried in the ground, which should help to reduce seismic and thermal noises. And also the distance of the arms will be about 2.5 times longer than the ones from LIGO. It is expected that this telescope will be ready in 2030. And then maybe some of you have heard about LISA, which stands for Laser Interferometric Space Antenna. And this will be a gravitational wave observatory in space. LISA will consist of 3 spacecraft. You can see it on figure 14 on this visualization. And these 3 spacecrafts are orbiting the Sun in a triangle formation. The distance between the spacecrafts will be about 2.5 million kilometers, and the sides of the triangle, the red lines on the picture, will be the arms of the interferometer. Of course, since there is a vacuum in space, no tubes are needed between these. And it is planned that 2 of these spacecrafts are used to detect gravitational waves, and the third one is used to monitor the system. And data processing is done on Earth with the signals coming from this third spacecraft. There is another advantage, that in space there is no problem of seismic noise, which makes it easier to even detect waves with very low frequency. There was LISA Pathfinder, the mission, which was to test some critical technologies for this LISA mission. And this Pathfinder was launched in 2015, where Professor Jetzer and his group also were involved in the whole project. So detecting gravitational waves in space will be a great goal that will hopefully be achieved in the next few years. And for LISA, it is expected that it will be launched in 2030. Now, thank you very much for your attention, and I'm looking forward to answering your questions. And here you can see the references that I have used for this presentation.